Hello everyone and welcome back to our Bison Data Science workshop session. Today we'll be talking about Pandas. I'm actually quite excited for this session because Pandas is an incredibly powerful library that really serves as the backbone for data science in Python. And as you can see in this image, this cute little panda is comfortable hanging out in a tree. And our goal is that by going through this tutorial, in the end, we'll be getting more comfortable navigating and also manipulating data with Pandas library in Python. So what is Pandas? Pandas stands for Python Data Analysis Library. It is the essential toolkit for any data scientist or analyst working in Python. And as we said before, Pandas is built on NumPy, which means that many of the data structures of NumPy are used in Pandas. But Pandas further extend the capabilities of NumPy. While they both have distinct strengths, they're often used together in data science workflows, with NumPy more providing the fundamental numerical operations and Pandas offering higher level data manipulation and analysis tools. So with Pandas, your data can live in structures which we call data frames. And by using DataFrame, it will make it much easier to organize, manipulate, and analyze our dataset. So for today's session, we'll be covering the basics of Pandas, from how to create data frames from scratch to import data, how to clean it, and how to apply different kinds of transformation. We will also explore how pandas integrate with other Python libraries. Specifically, today, we'll start by first understanding pandas' primary data structure, that is series and data frame, and then we will learn how to create these structures and bring data from different sources. After that, we'll get hands-on with data exploration, learning how to inspect and understand what's inside our data frames. We will also dive into indexing and slicing data, and we will be touched on working with state and times, which is an important topic in data science, especially for time series data. Finally, we're gonna wrap up with some data frame operations like how to add or remove data, how to apply functions, and combining data frames. So, to begin with, we need to first import the pandas library. The most important statement here is this one: import pandas as PD. So PD is kind of the standard abbreviation for pandas. And by importing it as PD, we can reference it very quickly in our code. So if we go ahead and run this code, now you can see that pandas has been imported in our in this Jupyter notebook. So now let's talk about the core components of pandas, or what pandas is actually built on. That is series. So a series, as we learned before in our day one on the data structure, so a series in pandas is essentially a single column of data, which is similar to a list or an array in Python. But the thing is that with the Panda series, we get additional functionalities like labels for each entry, which makes data manipulation much easier. And on the other hand, DataFrame is a table or a two-dimensional array made up of multiple series. So you can think of it like a spreadsheet, where each column can be different data types, and DataFrame allow us to store, organize, and manipulate our data very efficiently, with each row and column have its own label. So as we can see this figure here, when we combine multiple series, we got a data frame. So in this case, we have a series of apple and another series of orange, and each containing some values about these two fruit. And when we combine them, as what we would do in a spreadsheet, now they became a data frame that looks like just like a table that with labeled rows and columns. And an important feature of both series and data frame is the index. So the index is essentially a label for each row, and it helps us locate and retrieve data efficiently. By default, when we create a series of data or a data frame, Pandas assign an integer index starting from 0, consistent with Python. So it's like what we see in the left side of this data, starting from 0 until 3 in this case. And why I spend so much time explaining this is because understanding these two structures is really fundamental to working with Pandas, as they will allow us to store and interact with data in a highly flexible way. Now let's dive into some examples. So first, let's learn how to create our own series and data frame from scratch. So to create a series, we can simply pass a list of values into the function pd.series. For example, here we're creating a series from a list of numerical values, and this output will be a single column of data with an index to the left. So if we run this and print it, we can even see the data type is a float. And secondly, what's interesting about series is that they can also contain mixed data type. In this second example, we have a mix of integers and also a string value, as you can see here. And when we introduce a different data type, Pandas will automatically convert the entire series to a data type that can accommodate all values. So in this case, we can see that the data type here is an object, which is basically, you can think of this as a string. And now how to create a data frame. So there are different ways to create a data frames, but one of the most common way is using a list of lists, where each inner list represents a row in the data frame. So in this example, we're passing a list of lists along with also the column name. So here we're passing serial list, which in each list have 4 components, and then we passing also a column A, B, C, D. And then if we print this, we can see that we just created a data frame, and it has 4 columns named A, B, C, D, and we have 3 rows. Now let's take a look at another way to create a data frame, that is using a dictionary. So in Python, dictionaries are made of key value pairs. So and when we use a dictionary to create a data frame, each key in the dictionary automatically becomes the column name, and then each value associated with the key will becomes the data in that column. This is also a very flexible approach because it allows us to easily label our columns and organize data by category. So basically, this method is more readable and straightforward for us to understand. If we execute this code, we can also see that it returned basically the same data frame that we just created. Also, we have 4 columns, A, B, C, D, and 3 rows from 0 to 2. Okay, now let's move on to one of the most practical parts of data analysis, importing data. So while we can create data frames from scratch, in most real-world scenarios, you will be likely working with existing data files that you need to bring into your code. So Pandas provides several functions to read in data from different formats, but for this session, we'll be mainly focused on reading data from plain text flat files. Flat files are essentially text files where each line represents a record or row, and columns within each row are separated by delimiters, like commas or tabs. And as you may already know, one of the most common types of flat files is the CSV, or comma-separated value files. As its name suggests, CSV files use commas to separate values in each row, which makes it easy to store and transfer tabular data. So in Pandas, the function we will use is pd.readCSV. Python provides this function where if you are not sure or if you want to know more information about a specific function, you can always use the help function, and then you just put the method or the function within the parentheses, and this will give you the official documentation about this function. And if we just hit run this code, as you can see here, we got an extensive text of the documentation about this read CSV function, it also specifies the different parameters that you can put. So in your free time, you can check that, but don't worry about this, massive number of parameters. In most cases, these are optionals and allow us to customize how our data is read in. One of the key parameters though here is SEP, which let us specify the limiters used in the file. By default, SEP is set to a comma. But also, if sometimes the CSV is using delimiters like tabs or space, then we need to change the parameter. And actually, the only required argument for pd.readCSV is the file path, which tells Pandas where to find the data files we want to load. And with this simple setup, we're ready to start importing data and getting it into a format that's ready for analysis. Now, before we actually import a data frame, let me just quickly introduce the dataset that we'll be working on. So for this session, we'll be working with a real-world dataset provided by the Demographic and Health Service, or in short, DHS program. And this dataset was collected in 2024 in Ghana and focuses on household surveys that capture a wide range of indicators across population health, nutrition, and environmental health. So the DHS program is known for its high quality, nationally representative data, and making it valuable for research and policymaking. One of the notice here is that due to the licensing and data sensitivity, we have taken some steps to ensure confidentiality in this data. And we've done some pre-processing to randomly shift the coordinates and also anonymize identifiers like mother or household ID. And also we sampled 500 urban and 500 rural records and merged the subsets into the original dataset. This let us analyze the data while respecting the privacy. Now, to begin with, let's first take a quick look at some of the columns in this dataset to get a sense of what information we'll be working with. So this is, as you can see, this is quite an informative dataset. We have in total, I think, more than 10 columns. As you can see, we have the year, some features like if this household is rural or urban, their IDs, which country this is taken, and also some indicators about their nutrition like stunting, wasting, and also the height, weight, and BMI, also wealth index. And finally, we have also the locational information, so latitude and longitude. And this metadata helps us to understand the structure and meaning of the data, which is very crucial before we dive into any data analysis. So now, finally, let's import this CSV file into Pandas so we can start working with it. And we're going to use the pd.readCSV file, and what in this parenthesis is the file path to the DHS dataset, which is located under the Day2 folder and in the data folder and called Ghana 2024 DHS household filter.csv. So if we run this code, we can see that some of the few first and last columns rows are printed, and we can also see the columns as these different features. And one thing to note that in the parentheses of the read CSV function, here the dot slash refers to the current directory while this notebook file is saved. So it is referring to this, if you look at the left hand, is referring to this directory day2. And it's then going further, another going into the data folder and then reading this DHS 2024.csv file. And before we move on, I just want to quickly mention that data scientists spend about 60% of their time cleaning and organizing data, and raw data often requires a lot of preparation before it's ready for analysis. and often some of these must happen outside of Python to format data for import, but ideally, the majority of data processing can be conducted in Python. So now that we have located our data in the DHS data frame, let's take a quick look at it. Since the data frame is quite large, printing the entire table isn't really practical. Instead, there are some functions that we can use to quickly examine our data set. So first, we can use the DHS.head to view the first few rows. And running this, put a 1 will just display the first row. And similarly, we can use the DHS.tail to see the last few rows, which will show the last 5 rows by default. And both the head and tail function also accept a number as an argument. And this is a quick way to sample data from the beginning or the end of the data frame. And now you can pause the video and try to print the first 10 and also last 10 rows from the DHS datasets. Okay, moving on. So in addition to viewing data, Pandas also provides several methods to quickly understand the structure of a data frame. One of the most useful one is pandas.info function, which gives us an overview of the data frame, including how the number of records, column names, and also data type. As we can see, the result from this function gives us this summary table, which has the column names and also non-null count and also their types. So here in this table is some other common functions that we can use to quickly examine the properties of our dataset. So the df.index will return the index range, meaning the number of rows. And we can see that we have in total 6,884 in this case. And also the columns will return all the column names in a list. And then the ds.types will just return a series with the data types of each column and indexed by the column name. And size will tell us how many will tell us the total number of values in the data frame as an integer. And finally, the shape will tell us how many rows and columns we have in our data set. Now, going further, let's move on to indexing and selecting data in the data frame. So unlike regular lists or arrays, data frames in Python support indexing by both labels and the integer positions, which makes selecting data a bit more flexible but also slightly more complex than a normal list or an array. Here in this example, we're trying to access the last 6 columns and also last third rows using standard indexing, similar to what we'll do to an 2D array. But if we run this code, we're gonna see that instead of a value, we got a key arrow. And this is because Pandas treats data frame indices as dictionary-like keys, and this syntax isn't valid for a data frame. So to work with integer-based indexing, we need to use the df.ilog function that will select the data by its integer index position. So for example, in this case, we're selecting the third row and also the second columns. And as you can see that now it returns us the value of 0. And if we go back to the third row and also the second column before, if we go back here, we can see that this is the third row and also the second column. Exactly, this is rural. So besides just selecting a single value, the df.ilog method also supports slicing, which allows us to select multiple rows or columns. And the syntax is similar to how we sliced the NumPy array before. So basically, again, we use the column to separate the start and end step. And then we use the comma to separate between row and column. For example, In this case, we're selecting the last 6 rows and then the last third columns. And if we run, we're gonna see the subset. And if we want to instead select the first 5 columns in every 40 rows, this is the code that we will use. So the first one is selecting every 40 rows, and then the second after the column is the first 5 columns. And in addition to the df.ilog function, we can also access rows of DataFrame using df.log, which locates rows based on their labels rather than the integer positions. So unless we set a custom index, the row labels are the same as the integer index. Here, for example, the dhs.log 500 will retrieve the row with the label 500. And when we use the df.log function to select a single row, it returns as a series, where each column name becomes the index for that series, and this makes it easy to see the data in a structured labeled format. You can also assign a row to a variable. For example, here, if we are creating a variable named oneRow, and we're making it equal to dhs.log1, if you need to work with the first row separately. One thing to note here is that when slicing with the df.ilog, the stop value is inclusive, meaning that both, in this case, the 1434 and 1440 are included in the result. And as you can see, the beginning and the end. But by contrast, slicing with df.ilog is exclusive of the stop index. So in this example, we can see that it stops at 1439. This difference is a bit subtle, but they can be important, especially when we select specific ranges of data. So it's good to keep in mind the difference. And one important feature of Pandas is that data frames can hold columns with mixed data types. For example, a series might contain floats, integers, and even objects like strings within the same column. So unlike NumPy arrays, which typically require a single consistent data type, Pandas allows the flexibility which is particularly useful when dealing with real-world data. However, it is usually best if each column could have a single data type to avoid potential issues when we are running some analysis. Just something good to keep in mind. Next, let's continue with the indexing. So in addition to integer-based indexing with df.ilog or df.log, we can also access columns in the data frame using 2 other methods. The first one is the dot donation, and the second one is using the square brackets. So with the dot donation, we can access a column as if it's an attribute of the data frame. For example, here, the dhs.wells_index, this will just return the column as a series. Alternatively, we could also use square bracket, dhs.wells_index, which will give us the same result, also returning a series as well. But if you want to get a column as a data frame instead of a series, we can use double bracket. So here, just by adding another bracket, as you can see, in this case, the output became a 1 column or multiple row data frame. And this allows us to select multiple columns by passing a list of column names. For example, now we're creating a new div and we are taking here rural, urban, and wealth index out from the original DHS data. And by using this code, as you can see, now we're creating a subset from the original database, which only has 3 columns. So when accessing a single column, the choice between the dot donation and square brackets is more or less of a personal preference. However, there are occasions when the bracket notation proves particularly useful. So for example, you could access each row in a data frame by iterating through the df.columns, which returns an index object containing the columns as the string objects that can be directly passed to the index operator. Additionally, you may also find it useful to use the double bracket index to return a data frame object rather than just a series. Okay, as you may have already noticed, also our DHS dataset contains a fair amount of nons or missing values, and this is very common with real-world data and simply means we need to handle these values properly to ensure an accurate analysis. So in Pandas, the NaN stands for not a number and represent missing or undefined data. And handling non-values is critical for building robust analysis and models. And today we'll look at a few methods to identify, remove, or even fill these null values. So first, how to identify the NaN value? An easy way is that to just use the PD dot is none, and which will create a Boolean mask indicating true wherever an element is a none. So for example, if we run this code, it will create a mask over the entire data set. So as you can see, there are some false and true. So for true, meaning that they, like in this cell, the data is a non-value. And if you want to check which row contains the non-value, then we can pass another, we can use the DHS.isNum.any and use the axis equal to 1 parameter. And then this will return true for rows that have any non-values. And this will help us locate incomplete data and decide how to handle it. So in some cases, you may want to just completely exclude the missing data from our analysis. And the most common way to do this is to use the drop none function, and which will just remove rows or columns containing the null values. If we run this, we can see that now index number 2 and even number 4 was dropped. So we can see that this is dropping the rows that contains the null data. So by default, this function removes any rows with non-data, and it creates a new data frame without rows that contain missing data. On the other hand, if you want to drop columns with any non-values instead, again, you can use the axis equal to 1 parameter, and this will remove columns where any missing value are found and give us a clean data set in terms of columns. And here we only have, a lot of columns has been dropped and we only have left a few. Okay, now in most of the cases, maybe we don't want to drop the non-value and we need to do some kind of interpolation or to fill the non-values. Pandas provides some simple way to fill the non-data. For example, you can use statistics like mean, median, or custom value, and this will allow us to keep the data structure intact while dealing with the missing value. For example, if you want to replace your non-value with, for example, 0, you can use fill non function and then specify the value in the parentheses. And here you can see that all the non-value have been filled with 0, but this is something that you really need to think about because often in reality 0 means 0 is actually a valid value for a lot of variables. For example, precipitation and temperature. So 0 actually has actual meaning for that kind of temperature. So you must be cautious when you are trying to put any values into the num. And sometimes for some time series data or situations where we want a more refined estimate, we can also use interpolation with pd dot interpolate. And here is an example that you're filling the non-value with the mean of each row. So first, we're calculating the numerical mean for the numerical values, and then we use the fill non function again to fill in the data sets. And now you can see that these are filled with mean value. And sometimes, if we're doing a more sophisticated approach, especially for time series datasets, we may want to do some interpolation to estimate the missing values. And to do this, we can use the pd.interpolate function. And here we are using a linear method to interpolate for stunting, wasting, and the other variables. And you can see here the non-values has been filled. So moving on, in this session we'll also cover a bit about datetime objects. So many datasets, especially in environmental and time series data, include timestamps at fine temporal resolution, for example, hourly or daily. In Python, they are managed using the datetime objects. And the built-in datetime library is the primary tool for handling data and times. But there are also helpful packages like dateutil for parsing dates and pytz for time zone management. While we won't dive deeply into datetime objects here, but it is useful to understand some basics. And Pandas actually provides functions to handle datasets, of which is on the pd.dateRange function. So this function, simply as its name suggests, it will create a range of dates or a datetime index with a specified frequency. So for example, this code, the pd.range, from March 1, 2023 to April 2, 2023 will just create daily timestamp, as you can see here. And to generate timestamp at different frequency, for example, if you want every minute, then we can specify the frequency parameter, and this will give us the frequency every minute. And then if we want it to be per month, here, actually this has been updated, so we need to use ME, and this will specify the frequency per month. Okay. And for demonstration in this tutorial, we're gonna create a new column called date in our DHS data frame. And this column will contain pseudo timestamp starting from January 1st, 2014, and they will increment it hourly. So here is a breakdown of how this works. First, we're importing the packages from datetime to create timestamp. And then we're gonna specify the start time, as we know, from January 1. And then we're creating a new column, date, and then we're using this list comprehension function by adding I-hour to the start time for each row in the data frame. What this will do, in short, is that it will result in a list of hourly timestamp that match the length of the data frame, and we're assigning it. So as you can see here, we just created an hourly timestamp from January 1st all the way until the last rows in our column. And now let's demonstrate how to parse the date objects in Pandas. So now if we look at the dhs.date column, which contains the timestamp for each record, we'll see that although this value looks like date, actually the date time did not change. So I guess Pandas, this is a bit weird. Let me rerun this. Well, my guess is that Pandas, maybe for this version, is smart enough to automatically recognize such date timestamp too as a datetime object. And now that Pandas recognize the date columns at timestamp, what we can do now is to set it as the index of our data frame using the setIndex function. And this will replace the existing index with the date column and turn it into a datetime index. This is useful for time-based analysis because it allows us to access and manipulate date based on time more efficiently. So if we run this code, we can see that the index column has been converted to the date index. And we can verify this change by running the dhs.info function. And now we can see that the index has been updated as datetime index. And also one thing to note here is that because we set the in place equal to true, and this will let the datetime objects override the index column. And we've run the describe again, and running the describe just to also provide another way to check your data statistics. And now that we have the index, we can access specific attributes of the datetime objects. And if we put dhs.index.hour, this will just get the hour of each record starting from 0 to 1 to 24. And if we got unique, this will return us all the unique datetime values in the dataset. And to even further, we can also get the unique hour values. And we can see that we only have 24 here because a day only has 24 hours. So this is just a quick example of how you can use the datetime function to manipulate datasets in Pandas. Now let's get back to the actual DHS data frame. And we're gonna introduce a few useful operations that we can commonly perform on the Pandas data frame. The first one is the reduction operations. The reduction operations help us quickly calculate values like mean, median, sum, maximum, minimum, and standard deviation for each column. In this example, if we run the dhs.median, let's see. Actually we got an error. Why we got an error? Because such operations require odd include columns to be numerical, and here we are referring to the whole data frame. So now to demonstrate, let's first create an all numerical data frame named df, and then calculate the median of each column using the df mean. So if we just created a all numerical data frame, and now if we run this code again, we can see that df mean is giving us the median value of each column. And to retrieve the value for just a single column, you can also use the indexing to call the columns as a series. So as again, we can use either the dot notation or square brackets to refer to a single column. And here is the median of the BMI. We can also check the mean, the max, the minimum, the sum, and even the standard deviation. And furthermore, as you may already notice, there are lots of non-values in our DHS data frame. And the default of Pandas is to ignore all the non-values when performing computations. And this can be changed by passing skip none equal to false to the reduction method if you don't want to skip nuns. But in reality, skipping the nuns is often quite useful if we are quickly inspecting the data. So now, besides removing data, we can also add new data to our Pandas data frame. And we can easily add new columns using different types of data. Here are a few ways to add a column to an existing data frame. So again, now we're creating a numerical data frame, df, which has 4 columns, A, B, C, D. And here are just 3 different ways. So we can add a column from a list. We can also add a column from a Pandas series. We can even propagate a single value through all rows. And now we are adding, in this example, we're adding 3 new columns, E, F, G. And we can see that all these 3 methods can add new columns to data frame. Another way to add columns is to perform calculations on existing rows. So for example, here we can add a new column by converting values in the A, for example, if A is temperature in Celsius, we can convert it to Fahrenheit. And also here we're adding a new columns. The difference between column B and C, and remember these are all inter-column calculation. And now you can see that again, a new column has been created. And finally, we can even add a column based on a condition which will contain Boolean values, that is true or false. So for example, the df d20 plus is trying to making a rows where values in D are 20 or higher. And if in column D is 20 or higher, you will get true, otherwise false. And using the Boolean mask allow us to perform operations not only on rows that meet a certain condition. So for instance, if we want to subtract 20 from all values in column D that are 20 or higher, we could use this code which will apply a mask to only perform the calculation for rows where the df.d is more than 20. And then for those who does not fulfill this condition, it will just return us the null value. And finally, we can also use the df.insert function to insert a column at a specific index. So for example, if we want to insert a season column at the beginning of our data frame, we can use the insert function to specify the index position, 0 in this case, and also the column names, and then the list. And as you can see, now we just successfully add the season to the first column. And finally, except for adding new columns, you can also remove columns from a data frame. But when working with data frames, removing columns should be done cautiously, especially if you might need the data later. And as again, it is always a good practice to create a backup copy of your data frame before performing any deletion operations. So there are two ways. First, you can use the del, the delete keyword, to delete a column directly. In this case, we're deleting the column G. And if we print the updated df again, we can see that G has indeed been dropped. Alternatively, if you want to remove a column but keep its data, you can use the df.pop function. So this method will extract the f column as a new series and delete it from the data frame. And here the df.f contains the data from the column f. And as you can see, again, the f has been removed. And if we print the df.f again, we can see that we have a series. So in addition to manipulating individual columns, you could also apply a function to an entire series or data frame using the pandas function df.apply. Here, we are demonstrating an example where we have a data frame of temperature in Celsius, and we're going to convert them into Fahrenheit. So first, let's just create the df. And here we are defining a simple function that can return the temperature in Fahrenheit by inputting temperature in Celsius. And here, if we we use the df.apply function to apply the convert Celsius to Fahrenheit. And we can see that the column A has been updated into a Fahrenheit unit system now. And we could even apply this to the whole data frame. And this will just update all the columns. And now moving on, in data analysis, it is common to combine multiple data frames to create a richer, more comprehensive data set. And this can involve merging two data sets with identical columns or aligning data sets with complementary columns to add new attributes. And in Pandas, there are multiple methods to combine data from different series or data frames into a single object. And these methods include concatenate, join, and merge. First, we'll focus on the concatenate method. Now, let's take a look at a simple case where we have two data frames with identical columns. As you can see here, df1 and df2 are both data frames that contain the locational information on several global cities. And we have three columns, that is city, latitude, and longitude. And we will use the pd.concat function to append the rows of one data frame to the other. So in this code, the pd.concat will append the df1 to df2 along the row axis. And if we print this, we can see that, and now we have a merged data frame that has both the rows from data frame 1 and also data frame 2. But as you may notice, the original indices from each data frame are also retained, as you can see 0, 1, 2, 3, 0, 1, 2, 3. So it is often useful to reset the index after concatenation to make it sequential. And we can actually do this by either using the ignore index equal to true with the pd concat function. This will tell Pandas to ignore the index label. Or we can call the reset index function on the resulting data frame, and to set the drop equal to true will prevent the old index from being added as new column. So if we run this code, we run the reset index function, we can see that now the index has been updated and it is sequential. And now let's look at a case where the data frame have different columns. In this example, we're creating a df3 which now has two columns named country and also elevation. And if we just trying to concatenate with the CT coordinates that we just merged, we're gonna see a lot of non-values for missing data. And here, this is because the F3 have different columns, that is country and elevation, than the city coordinates data frame. And Pandas will automatically fill these non-matching cells with non-value for missing data. But if we look at it more closely, we'll likely that the original idea should be that to concatenate the df3 as column. So we're gonna have the first Los Angeles, USA, the elevation, and then Bamako for Mali, and then Johannesburg for South Africa. To do that, if we want to concatenate along the axis, what we need to do is just, again, we add the axis parameter and set it as equal to 1. And then now, if we run this code, we can see that the column data frame has also been concatenated along the columns to our city coordinates data frame. So besides concatenate, we can also use the merge and join function to combine information from different data frames based on shared columns or indices. And this is particularly useful when you have data from multiple sources that you want to bring together for more comprehensive analysis. And in this example, we're going to use health data and health and facility data from different regions and demonstrate various join types in Pandas. One thing to mention is that although both merge and join can use to combine two data frames, the main difference is that the merge function is used for column-based join, but the join function is mainly used for index-based join, and that's less flexible. And in the following example, we will demonstrate how we can use the merge function because we'll be using common columns to perform the merge. So first, let's create two data frames. One is health data, which will have different regions in Ghana and also the health conditions. And then for the second data frame, we're gonna have the different health facility data, so the number of hospitals and clinics. And now if we look at these two data frames closely, we're gonna see that they both share a common column, that is region. So, and that's the key where we're gonna use to join the two tables together. So to join these two tables into one with the merge function, we can apply different types of join. So the first one is the inner join, which is also the default. And an inner join will only include rows with matching keys in both data frames, and it will excluding any regions that doesn't appear in both. And if we use this, we're gonna see that hospital and clinics has been joined with the health data set. And to perform an outer join, So in the output of the outer join, we can see that we have some non-values for central and eastern. And this is because the central is specific to the health facility dataset, and the eastern is specific to the this is because the central is specific to the healthcare facilities dataset, and eastern row is specific to the health condition dataset. And because they're not matching, but anyhow, outer will still include all the rows. So for the columns that has no data, it will just put none in this case. And the left join will include all the rows from the left datasets. In this case, it will be the health condition data frame, and only the matching rows from the right, in this case, the facilities. And if we see, we're gonna see that the eastern is showing in our result, but since it does not have any record on our facility dataset, the value here is stored as none. And similarly, a right join is just the opposite of the left join. It will include all rows from the right data frame and only the matching rows from the right data frame. And here we can see that only central is here, but not the eastern, and because central does not have any data in the health condition, it is still recognized as none. And moving on, while Pandas is often used to manipulate, analyze, and visualize data with Python, there are situations where it's beneficial to also export your data frame after processing. And this can be useful for sharing your result, saving intermediate dataset, or just loading processed data into another application, such as GIS or R. And here, if we want to export the city data frame that we just created in our previous section, suppose we want to save this data as a CSV file to be loaded into another software. We can use the pd.toCSV function in Pandas to export the data frame. We can just do this by specifying the file name and also the path. For example, if now I want to specify to a CSV, and I just put city.csv, and if I run this code, we're gonna see that if we refresh the page, we can see that we just have a new output CSV named cities, and if we click, we can see that this is the data frame that we just created in this code. So this is as simple as this. And another important thing to remember is that when working with files in Python, especially in data analysis or file manipulation tasks, it's common to manage file paths. And handling file paths correctly becomes crucial in collaborative projects because the code might be shared or run on different operating systems or different devices. So let's try to break down some basics and see how to join file paths. So first, there are two types of file paths. The first one is the absolute file paths, which are the complete paths from the root of the file system to the file. Like, for example, C drive, then user's username, document, file, text. The second one is a relative path, and these paths are relative to the current working directory, such as the ./data/Ghana.csv. This is referring to the current working directory of this active Jupyter notebook. And instead of manually combining strings to create paths, which could lead to errors like double or missing separators, we can use the os.path.join function, and this method automatically adjusts path separators. For example, Mac use slashes and Windows use backslashes. This function can just adjust the path separators based on the operating system and ensuring your code runs smoothly across different platforms. So in this example, we're trying to use the os.path.join to get the full file path to the CSV file within our data folder. And we can do this by first specifying the absolute file path to our base directory of this workshop, and in this case I saved it under my C drive users, Ghana workshop April, and then under the Climate House Data Science workshop folder. And now the second one, the file name is the relative location path within this whole working directory. And as we know, this is under day 2 and under the data folder, and this is the DHS prevalence WC cover CSV. And then we just use the join function to join the base directory path to the file name path, and we can print the full path. And if we read this CSV file and add it as a Pandas data frame, we can see that this data has been correctly loaded. And once again, using the OS path join function is really good when you are collaborating with other people on the project, because you just need to change the absolute path to your base directory and the relative file name will stay the same. And now that's all for today's session. I know this is a bit of too much content, so please spend as much time as you need to go through the Jupyter Notebook, the code, and also here are some examples. And I would highly encourage you to try to practice the code and then to answer all the questions in this. And I believe this will really help you to increase your coding skill. And that is for today, and I look forward to seeing you in our next session.